Well, last hour we were talking about that wind setup, and I had begun describing a simple computation of wind setup, which must be regarded as simplistic. There are two things that that need further attention. One is the shear stress on the surface due to the wind. Recall I provided a simple relation. The shear stress on the surface of tau sub s was equal to 3 times 10 to the minus 6 u squared over g. Well, this number has been subject to a lot of controversy. Obviously, that's an empirical coefficient. And the problems that arise are due to the changes in roughness of the sea as the wind increases. If the wind blows on a perfectly smooth surface, you can imagine that the shear stress applied to that surface is less than when there are waves on that surface. Well, the problem is that the wind generates the waves, so you expect a nonlinear process. That is, an increase in friction as the wind increases, because the wind increases the roughness of the surface. There's another complication too, and that is that if the wind is dry, that is, it comes off the land, for example, and it has relatively low humidity, then it takes up moisture from the wind surface, and the density of dry air is about 29. 29. I'm sorry. The molecular weight is about 29 grams per mole, and the molecular weight of this is of air, and the molecular weight of water vapor is 18 grams per mole. So the moisture, because the air pressure remains relatively the same, when there's more moisture in the air, its density is less. And if the moisture is arising off the surface, then it'll have lower density and it'll tend to be buoyant and enhance the mixing, the momentum transport processes near the surface of the water. So that, on the other hand, if the air is all moist, as if it had blown for some distance across the ocean, then you expect relatively uniform density with depth, and the momentum transfer processes then would be more like stable air, be normal. These two problems, the change in roughness of the surface with the change in wind velocity, and the difference in moisture content as for a wind blowing off of dry land, cause uncertainties or cause changes in the shear stress, effective shear stress of the wind on the surface.
I have in my notes that equation, I have tau.
Oh, over rho g. Yeah, you're right. Thank you, Jamie. So that 3.0 times 10 to the minus 6 needs to be considered back in the envelope type number. You need to look into it further. Now, I passed out two papers, one of which I'll have to make more complete. One was done by Professor Amorocho and Professor DeVries. I don't suppose any of you knew Professor Amorocho. He was professor in this department. But Professor DeVries is still around, and his data came from measurements of wind stress on a canal on the California aqueduct, actually. And they came to the conclusion that the wind stress increases with the increased velocity of the wind, with the roughness, up to the point where the waves break. And when the waves start breaking, then the waves dissipate the wave energy by breaking, and they don't get any higher. So they proposed an increase. They used a logistic relation, which is given to you. An increase up to some maximum value, and then above that value didn't increase any further. And their argument has a lot of merit. That kind of a description has a lot of merit. The problems that you run into in wind setup usually have to do with unusual conditions, hurricanes, typhoons in the Pacific. And there you have a complex situation with rainfall and low pressures in addition to the shear stress on the surface to contend with. And this issue of whether the hurricane, whether the shear stress on the surface resulting from the winds in the hurricane increase linearly or add some maximum value turned out to be a turning point in the modeling of hurricanes. We did a study some years back on hurricanes in the Gulf and along the Atlantic coast. And that roughness, as you can imagine, has a major impact on how high the water surface was as the hurricane came on shore. Our problem is that there are very few measurements, very few actual measurements of water surface elevation resulting from a given wind field. I say we, it's a committee I participate in, recommended strongly to the federal government that they put measuring devices along the shore where hurricanes are likely to come on shore so that we can get some data and verify these models. There are about 3 models that are used now widely for water surface elevation under hurricanes, and the 3 of them don't agree very well on the numbers they give. And huge amounts of money, are spent on protection works. Every foot of a seawall costs millions and millions of dollars, along its length. So this matter of water surface elevation under wind stress is a serious matter. Well, that recommendation was made, I think, 1982 or 83. And the government had teams of people to do that, but they never could coincide with a hurricane. And last year they gave the program up. We were pressing to have them keep trying, but the hurricanes are so unpredictable that they can't get their measuring equipment there in time to get the data. So I have to say that there's still a lot of uncertainty in wind stress on the water surface. The papers that I passed out are the best I know in describing that. The other problem, that is what the shear stress is on the bed, is complicated by those factors, that return flow. But usually the return flow is very much lower than other currents. Recall I drew a profile of the bed that looks like this. The shear stress due to this return flow is usually quite small. That 1/10 of tau s is just a kind of a rough number, but it's usually very small, and it doesn't affect the erosion of the bed very much. But it does affect the direction of transport. That is, if the waves are stirring up the bottom, and there is even slow motion of this sort, then it can carry large quantities of sediment. So this tau resulting from this isn't too important as far as sediment transport is concerned. It is important as far as calculating wind setup. Remember that. We also, I should point out that the other factors that determine the current are the resonance that we talked about, the tidal current, and the oscillatory motion under waves. The tidal currents I've only alluded to, and I should say a few more words about that to clarify them. The reason that tidal currents occur is that the ocean surface rises and falls. The effect of the sun and the moon on the water in the estuary, you can forget about that. The problem is, or the source of the tides and currents in an estuary are the rise and fall of the ocean at the estuary mouth. So when the ocean surface rises due to the tides, water flows into the estuary, and when the ocean surface falls below that of the estuary water, water flows back out. I'll show you some examples of that presently. But the point is, you can regard the mouth of the water surface elevation at the mouth of the estuary as one of the boundary conditions, and not worry about the sun and the moon and so forth as far as the interior of the estuary is concerned. And of course that makes the water in the estuary flow in a progressive tidal wave up through the estuary. And the amplitude of the wave is damped due to friction in the estuary as it progresses up through the estuary. And I'll give you some examples of that in just a few minutes. I'd like to turn to the topic of fresh and saltwater mixing that goes on in the estuary, because this so-called mixing zone is an important process, or the processes in the mixing zone are important in an estuary because they control sediment transport, salt transport, and play a big part in the biological system in an estuary. If you consider first of all a system that has very little tide, so we can just look at the river saltwater mixture, then let's say something like the mouth of the Mississippi, which is a long delta. New Orleans is way up here somewhere, and this has a couple of passes in it in the delta out here, out into the Gulf. The tide range here is about a foot, or perhaps just slightly over a foot, so there's very little vertical motion in the Mississippi. And the water flows are appreciable. Flows during the summer sometimes, or right after the snow melts, can be as much as 900,000 cubic feet per second. Really a large volume of flow. In that case, where you have a large freshwater outflow and a small tidal amplitude, you have very little mixing. And the result is, if we draw a profile along along the axis of the estuary, of the outflow here, and I'll expand it vertically like this. Actually, I should go more realistic, where I've exaggerated the vertical scale. If this is the ocean end, and this is the land end, the seawater, and note that the dimensions of this are nearly constant along length, that is, the width is nearly constant along length, and the depth varies as I showed here. And what you find is that there's a pronounced saltwater wedge, where this is salt and this is fresh. And this wedge moves only slightly and has a very sharply defined interface. If we plot, let's say right here, on this section here, if we plot the density versus distance above the bottom, what you find is that it's the density of fresh water, and then at this interface, it increases very sharply, and then it's almost constant from there down. Let's call this interface 1. So this would be 1. And if we go down further, call this interface 2, then what we find is that it looks like this. Very sharply defined interface. There is sometimes at high flows, high freshwater flows, there are some waves that break on this interface, and there's a little bit of mixing there. While it's sharply defined, these waves can occur. And the result is that there's a net flow, a slow net flow landward in the saltwater wedge, and a much stronger freshwater outflow at the surface. Well, this is the case in the Mississippi River. In most estuaries, however, there's a significant tide. In San Francisco Bay, the mean tide range is about 4.4 feet. So the mean tide range is about this much, and the spring range is not quite twice that amount. So you can see there's quite a bit of flow in and out of the Golden Gate. And in that case, the estuary, before I get away from this, these bottoms, when the freshwater flow changes, if it is reduced, the saltwater wedge will move inland, and if it's increased, the saltwater wedge will move outward, particularly right in this region here, where the cross section changes a little bit with distance. When it moves outward, it often leaves a little pool of salt water in the depressions. I've exaggerated this because of scale, but it'll move out and leave this salt water, and the fresh water will flow over it. It'll just stay in this depression. This saltwater wedge problem affects water supplies upstream. New Orleans takes water out of the Mississippi and treats it, and so do smaller towns along the river. And if this wedge moves up into their area, then they get salt water in their intakes. A year before last, during a very low period of low flow, the river moved upstream and threatened these water supplies, and the Corps built a gravel sill, a low dam, out of local gravel in the estuary, and stopped the wedge at that level and saved the water supplies upstream. Then when the high flows occurred again, they just washed this wedge out. It sounds simple, but stop and think a minute about all the things that were involved. First of all, they had to know that the wedge would be, that the sill, would be high enough to do some good. And they had to know that it wouldn't be overtopped by the salt water going out. Second, they had to know that it would stay there during the flows under concern and wash out later. They determined those things by model studies, physical model studies. And because the situation developed quickly, they had to move fast for a government agency, and they built the whole thing in 1 month's time. They saved, the savings and cost was incredible. If the city was without fresh water or had to bring fresh water from somewhere else, it would have been really a major problem. Well, that's kind of a sideline. In an estuary where there's a significant tidal current, the situation is a little bit different. This is idealized. But this, instead of having a wedge like this, the wedge has to move back and forth with every tide, with every rise and fall of the ocean. So that in the process, this moving back and forth, together with the roughness that's on the bottom, cause upward mixing of the salt water. So that you have a fuzzy, if you like, or a mixed apparent wedge where there's a net landward flow in the lower region. I've exaggerated that a little bit, but something like this, and a net outflow in the upper region. And the salinity, it's mixed, and the salinity is difference between the top and the bottom may be about 3 parts per thousand. That is not very great. Typically 2 to 3 parts per thousand. Up here, the salinity might be, say, 20 parts per thousand, and place, and down here it'll be 22 or 23 parts per thousand. Not greatly different. And up here, and because of this mixing process, here it may be 2 parts per thousand further up here, and down here maybe 5 parts per thousand, and so on up the stream. So what happens is that as you go landward, the salinity decreases throughout the water body, but it maintains a difference between the top and bottom. Now this small difference, sometimes it's smaller than that, maybe 1 or 2 parts per thousand. This small difference led modelers to believe that they could model this as, early modelers I should say, model this as a vertically mixed system. That looks like a small difference. But it turns out that even that small difference causes a net landward flow on the bottom, an upward mixing of the more saline water into the pressure water, and that combines and adds to the water flowing seaward. So there's a net circulation in this way and back this way. The amount of that Q, if you want to call it Q ocean, divided by Q fresh, is on the order of 10. That is, the amount of ocean water that comes in and mixes upward and goes back outward is often as much as 10 times over this whole mixing zone. 10 times the amount of freshwater outflow. You can see the implications of that for water quality management. It means that there's a huge amount of dilution that takes place of the river water that's due to the fact that the ocean water is coming in and mixing and going back out. It's lost, of course, if the freshwater flow is diminished to the point where you don't have this. I'm going to show you a little bit about that. As the freshwater flow is diminished for a given tide range, this will typically move up into the system where the cross-section is less. So that reducing the freshwater outflow will reduce the amount of this mixing that takes place and move the whole system farther up into the system. You can see immediately the implications as far as water quality management are concerned. No? When the tide range, small, I'm going to say more about this in just a second. Small tide range. Relative large freshwater flows. And this is larger tide range. Smaller freshwater discharge. This is the more typical situation. The Mississippi is an unusual situation. This is much more typical. These are referred to as stratified estuaries. And these are referred to as mixed estuaries, or partially mixed. But really, well, I'm going to give you some criteria in a minute. Really, the only distinction is degree. There are sometimes small amounts of mixing on the Mississippi, although it appears to have a sharp interface. If we plot the density here as we did there, let's say up here, what we find is something that looks like this. Usually there's a layer that's about uniform density near the bottom. And if we do it up here, what we find is something like that. I'm going to give you some numbers, yeah. But qualitatively, when you have a small tide range, so there's little disturbance by the ocean, at the ocean end of an estuary, and a large freshwater outflow, the effect of the freshwater outflow dominates the system. Okay. When you have a larger tide range, then you have the combination of the two boundary conditions affecting the mixing of the system.
For example, on the Sacramento River, how far upstream does this mixing occur?
That's a good question. Can I enlarge a little bit? There's a question in regulatory agencies of what, and amongst some scientific people, of what constitutes an estuary. And my definition, which I think most people subscribe to, is it's the transition between the unidirectional freshwater outflow and the tidal saline ocean, and everything included in that is called an estuary. The increase in salinity will go up quite a large distance, and it changes, of course, with freshwater outflow. During floods that I've observed, it may go clear down in the sand double water outflow. During drought periods, like now, it goes up to Chips Island, a little bit above Chips Island. That is the western edge of the delta. That's the salinity. But the tide actually, during low flows, goes on up to Nice Landing. You know where Nice Landing is? So from the standpoint of the tide, not much of a tide at Nice Landing, but a small variation in water surface. At low freshwater, at higher freshwater outflows, the tide's much further down. The noticeable tide much further down. So the upper boundary moves back and forth with the freshwater outflow. The seaward boundary appears to be fixed at the Golden Gate because of the constriction. But actually, this freshwater outflow turbidity that comes along with the flood flows, I've seen out at so that even that boundary can shift. I hope later to show you some San Francisco Bay pictures that help with that. Well, with this qualitative description, I'll give you some notes that people have recommended for classifying estuaries. Now, the motive for classifying estuaries is to try to put some kind of systematic description so that you can communicate. But in fact, that is, there is a continuum of ranges. In some, the mixing is very, very strong in the Thames and the Gironde and the Severn, and those are good examples. Where the tide ranges on the order of 8 to 10 meters, with a really large tide range. Then, as you can imagine, this mixing is profound. I mean, they're very well mixed. Let me give you some examples of these classification screens. If we describe the volume of fresh water outflow per tide period divided by the volume of the tidal prism, where the tidal prism is the volume that results from the rise and fall of the tide. That is the change in volume of the estuary with the rise and fall of the tide. And for that, they take a mean tide for the tidal prism. When this is greater than about 0.8, it's called stratified. And well mixed, it's less than 0.1. And in between, it's called partially mixed, of course. Now, that's a pretty rough kind of a description. Harleman and Ippen, two professors at Massachusetts Institute of Technology. Professor Ippen no longer living, but Professor Harleman is still pretty active. They gave an estuary number. And that is the P sub f, I'll define these in just a minute, divided by F sub O squared, divided by QF, freshwater outflow, times T. This is the tidal period. That's the freshwater outflow. Discharge. P sub F is the tidal prism. And the F is the Froude number. Densimetric, or the Froude number, equals U, where UO is the maximum flood tide velocity. Divided by the square root of GD, or GD, where D is the average depth. And this is regarded as estuary number. And this is regarded as the ratio of the energy dissipation per unit volume divided by the gain in the energy at due to the freshwater outflow per unit volume. Well, they give these numbers, and they've used these to just classify estuaries. It's not, there is no firm relation. It just what it does is give you a range of conditions between the one I erased and this one that they have used to classify estuaries, and I wanted you to know what it was so that if you saw it in the literature, you'd recognize it. Another relation given by Harleman and Ippen is the velocity predominance. Before I give you that, I better describe velocity predominance for you. If we look at this diagram, and say we measured the currents along some section here from top to bottom, what we would find is, and we measured them throughout the tidal cycle, what we would find is that at the top, let's say at position A, at A, what we would find is that there's a very large, this is flood, and this is ebb being toward the sea. What we find is that the ebb would be very large compared to the flood. Looks something like this. That means that there's more water flowing out at near the surface than flows back upstream. That fits in with the secondary circulation pattern that I described, or gravity circulation. Now, if we measure it down here at the bottom, call it B, what we would find is that the ebb would be relatively small, and would last longer than the flood, but there would be, I didn't make that quite large enough. There would be more flow upstream near the bottom than downstream near the bottom. You follow me? So if we look at the area, this area here, that's the distance that the water flowed upstream. The velocity, this is u, the velocity. The velocity times time is the distance the water moved, right? So we can take this area A and this area B, let's say for one of those, and plot what's called the ebb predominance. Which is equal to ebb A divided by A plus B. The area is A over A plus B. And this is the distance up from the bottom. And at the surface, what we would find is that, let's see, we better call this, this is 0, and let's call this flood and this ebb. At the surface, there would be very much ebb predominance, and it would look something like this. That is this is A. I'm sorry, at this location. I don't have that quite right. Where A is about here, and B is about here. And in between it would look something like that. So if we measured it at a number of points, number of elevations, we would get a curve that looks something like this. If we were to go further upstream and make the same measurements, we would get something that looks like this. That is, if we were to go to position 2. This crossover point is the point roughly at which the net upstream and downstream flow is the same. Have I confused you? I see a lot of blank faces. Let me go run through that again. Is what? Ebb and flood. Let me write it down again for you. We'll start with a clean slate, okay? We have a mixing zone. I'll draw the region of mixing, something like this. And let's consider location 1 and location 2. And recall I said there's a net inflow near the bottom, upward mixing all along this region of mixing due to the back and forth motion of the water resulting from the tides and friction of the walls, and a net outflow near the surface. Something like this. If we measure the currents here, that's at 1, as a function of time. And this is ebb. Oh, this I called flood before, isn't it? Yeah, flood. And this is ebb. Velocity, ebb velocity. Okay, velocity during ebb. Ebb is when the water is moving toward the sea. Flood is when the water is moving toward the land. Okay. Then near the surface at location 1, the flow is predominantly ebb. That is, the river water is flowing toward the sea near the surface more than it's flowing toward the land. So during a tidal cycle, the currents now would be ebbing at the surface, and the ebbing at the surface would be more pronounced than the flood. That is, there's stronger flows during a tidal cycle near the surface than there is flooding flows. So this is 1. This is 1A. Okay, right near the surface. That's in 1A. Here. Before I go on, I'll redefine this. If we plot U at E, a flood and an ebb, this is 0. With time, then the call this A, this area here A, and this area here B. Then we call a flood predominant, or ebb predominance. Is equal to A divided by A plus B. This is A, area A. How does that go? That's the distance that it moves. Okay, now if we make a measurement down here near the bottom, well, I'll make 3 of them. We'll call this B and this C. Okay, 1A, 1B, and 1C. Now if I look at B, then you'd expect something a little bit different. See, near the bottom, it'll cross something like this. And then if you look at 1C, what you'll find is that it'll actually come across like that. So if we look at here, no, they don't. In fact, there's a time during which the water is flowing upstream on the bottom and downstream on the top, and it may be an hour or so. This is time in this direction here. The tide oscillates the water surface. The currents that result from the tide have to do with the slope of the energy gradient. And the energy gradient, I'm getting a little aside here, but I think it's useful. If we look at distance up the estuary again, where we have some kind of a gradient in the salinity here, if you plotted this potential energy, then you'd have, because of the density change, you'd have an increase in pressure, hydrostatic pressure, like here. But at this point, it would begin to, the slope would change, wouldn't it? So we'd have this is the ocean out here. We have instead of a straight line hydrostatic pressure, we have a change like this. Down here, it would look like this. I think I've drawn that pretty well. So that while you may have a slope in this direction at the surface, at the lower part of the elevation, you may have a slope in this direction, a pressure slope in this direction. So right at the change of tide, a change as slack tide comes by, what happens is at first the change occurs at the bottom and then later at the top. I'll show you some actual data presently. I may not get to it today, but so you can see what happened. But the problem is you're dealing both with a change in slope of the water surface due to the tides and a change in the hydrostatic pressure distribution due to the stratified density of the system. You follow me?
One more question about the axis of time and that. Is that real time, like time zero, you start with each curve, or you shift it as they all start?
Let me show you some real data. Because it's different on ebb and flood, changes on ebb and flood. So just hold that for a little while. I'll show you some actual data. Well, now, if you plot for each of these curves, the ebb predominance, and you'll see the significance of this presently. This is 0. Well, let's see. I guess probably I'd better put this in terms of a fraction, so that would be 0.5, the way I defined it here. Before I get away from it, the last number produced by Ippen and Harleman is velocity predominance following this kind of an argument. And that's the average velocity u over tidal cycle divided by the freshwater inflow velocity. Q over A, where A is a cross-sectional area of the body. And what they found, and this is UV, near the bed velocity, averaged over time, divided by the freshwater inflow velocity, I'll call it V sub F. And what they found was that if you plot for a number of estuaries, U sub V over V sub F, against the densimetric crowd number on a log scale, we'll call it X like this, where the densimetric crowd number is equal to the freshwater flow divided by the square root of delta rho over rho at X times GH or GD, I used before, where f of X, this is X from some seaward distance. What they found, seaward location, what they found was that there was a relationship between these two with distance, with with, that would occur along the estuary. And at different points along the estuary, there would be a relation like this. And if you plotted this bottom velocity predominance, UB, or this is X, and this is UB, predominance, just determined the same way we did before, that there would be a decrease with distance up the estuary, and the net value would be something like this, so that the null point would occur at some point X up the estuary. If you want to look further into this, we won't go back to this anymore. I just wanted to show you the correlation. You should see that book by Eppen that I referred to before, estuarine hydrodynamics. The reason we won't go into this further is that it's been pretty much superseded by modeling, and we'll talk about that. But you should know about it for historical interest.
On your diagram, what is the horizontal line?
That's the 50% point that I had. Thank you. That, just like this null zone that or this ebb distance predominance that we described before. Well, I had planned to show you some pictures, and I think what I'll do is save the pictures for later, but show you a couple of slides, a couple of view graphs that give you some idea of the. This is a plot of salinities in the San Francisco Bay. Measured in the San Francisco Bay system for different freshwater outflows. This is Carquinez Straits, this deep part, and this is a profile from Carquinez Straits up toward Chips Island. Chips Island is up here. Now, what do you see up there? Chips Island is right there, so you can relate this to the position in the western delta. And this is Carquinez Straits, this deep spot. The vertical scale is exaggerated. The top plot is for freshwater outflow of 64,000 cubic feet per second. The freshwater outflow index is a computed freshwater outflow based on a summation of the river inflows into the delta minus some supposed evaporative losses or consumption in the delta. And if there's flow out through the Joel bypass, that's included. So it's a computed by difference freshwater outflow. It's an error sometimes at high flows, but it's a reasonable estimate. The problem is you can't measure the flows very well in a tidal system. You measure differences in it. You can see that with very high freshwater outflows, this salinity is fresh, that is, the water is fresh down to Collinsville, say, about Collinsville. And then the change in freshwater outflow, and change in salinity, rather, increases rather rapidly. Remember, seawater salinity is about 33 to 34 parts per thousand. So you can see this is nearly seawater salinity right at where it enters San Pablo Bay. The bay widens out and the seawater can intrude more easily there. At high freshwater outflows, and then as it's reduced down to 20,000 cubic feet per second, you'd expect it to move back upstream. Now let's see, that's May. I don't know why it isn't, but it isn't. That doesn't seem, oh yes, it is. This is 0.15, and this is 0.5 here. We just don't have the rest of it. Then at 13,000 cubic feet per second, you can see it's moved upstream, 0.15 is near Chips Island. And then at later on, it took apparently some time to move upstream, or the history between September and August of 94, it hadn't yet readjusted. This is 1 part per thousand, so 0.15 was way up here somewhere. And here it is, 3,600 cubic feet per second. 0.15 was up here somewhere. And at 800 cubic feet per second, it's definitely up in the delta somewhere. So you can see that as far as salinity, the position of the front changes with freshwater outflow. Also notice that it's spread out more with low freshwater outflows than it is with higher freshwater outflows. It tends to be bunched up. Now it takes some time to adjust to a change in flow. That's not reflected here, but it doesn't take very long. Andy?
You were mentioning that on the freshwater side, on the downstream side for September and August there, with the same indexes.
That's above seawater. There's evaporation on San Pablo Bay. That's called a negative estuary when you see that. South San Francisco Bay is a negative estuary. There's more flow into it than out because of evaporation. Similarly here, August. Well, it's spread out. This is the dotted area is referred to as a mixing zone. Actually, it extends out here. And I think this is well, this is related to some other data. The important thing is the salinity, to see how it moves upstream with lower freshwater outflow, and how the change in it, that is, it tends to spread out. The shrimp that I mentioned to you that are food for striped bass are distributed this way. Notice these are, I think these are numbers per unit volume, but it doesn't say what it is. The bar graph indicates, however, that at an outflow of 64,000 CFS, remember it was pushed down this way, they're bunched up in a small area. Remember also that the length of the mixing zone was shorter. With lower outflow, 13,000 CFS, they're spread out a little bit more. With still lower outflow, they're moving upstream into near this null zone. And with still lower outflow, 800 cubic feet per second, they're all up in the end. And notice there aren't as many of them. So you can see that there's a direct biological connection. This is neomyces shrimp, but the same thing is true for different kinds of algae and other organisms. The algae picture is complicated by the presence of Suisun Bay, which is a large, shallow bay, fairly large, shallow bay. And it appears that the algae multiply there, but their numbers are affected by filter feeders, mussels and clams and so on. Clean them out. Well, I don't want to get off into water quality just yet, but to point out that it is important there. Now, from the standpoint of sediments, I'm going to show you this at a later time. This mixing zone can be described this way. This is the ocean, the upstream end, and the ocean end of the far end. We have riverborne suspended particles, dispersed particles coming into the system and mixing downstream and settling in the large shallow bay or downstream. During windy periods, they're resuspended and carried upstream with a net upstream flow and deposited each slack water when the water reverses direction. And as I'll show you later, they may deposit and be resuspended, but the upstream motion is farther, remember the flood predominance, than the downstream motion. So there's a rectification, that is a net flow landward near the bottom. And these are heavier aggregates that tend to settle in the bottom, but they're of course mixed upward, and the finer particles, the finer aggregates, mix up more easily than the coarser ones, but they mix in with the riverborne suspended particles and aggregate with them, large numbers of particles and a few larger particles, so it promotes aggregation. The velocity gradient in this whole region is high because of the density gradient. I'll show you this again. So that aggregation is favored in this region. Well, this process, and of course the ones that aggregate go down and settle and go back into this system. So we have a trap. That is, if the particles can settle somewhere downstream, then they're carried back upstream on the bottom, near the bottom. And if those that mix upward are carried back downstream. So we have a gravity circulation not only of the water, but also of the sediment. You can see that the long times involved, repeated cycles, combined with a relatively higher, but not too high, velocity gradients in this region, promote aggregation of the particles and tend to trap it. Well, I want to show you a couple of estuaries the next time we meet to give you some concrete examples of these. Before we disband, I have to go to Washington for a committee meeting this coming week, and Dr. MacArthur Robert. Will present a lecture on Tuesday on hyperconcentrated flow. That's supposed to come at the end of our course, but it's convenient for me to have him come in now. So if you'll excuse the change in pace, he'll come in and show you some videos and describe problems. It's particularly relevant now because of the Pinatubo landslides and the more recent floods in the Philippine Islands. The floods combined with landslides killed something like 3,000 people, last I heard. It's a major problem in South America, all along the west coast of the United States. And we've only recently made progress in predicting these mud flows. This is cohesive sediment transport in a catastrophic situation, if you like. The mud flows down at high velocities and causes huge losses in property and life. In any case, he'll come and he'll have videos and so on to show you. And he's knowledgeable in this area, so don't hesitate to ask him questions. And I'll be back on Thursday.
What was the volume of the tidal prism? Is that the wedge of salt water?
That's the change in the volume due to the change in water surface elevation. So it's a change in volume of the estuary with the tide, with the mean tide.
Is that measured from low tide?
It's a mean it's the mean range. You take the mean high water and the mean low water, and it's the difference in elevation, the volume between those difference in elevation.
Here's the question we had before over there. When you had your